May 1941, 30,000 feet above the Mojave Desert, Major Signa Gilkey pushes his P-38 Lightning into a steep dive, testing the limits of America's most advanced fighter. At 320 miles per hour indicated airspeed, the tail begins shaking violently. The nose drops. Despite full back pressure on the controls, the aircraft steepens into an almost vertical plunge. Gilkey has entered a realm where physics turns hostile, where the very speed that makes the P-38 lethal also threatens to destroy it. The Lightning was supposed to be invincible. Twin Allison engines delivering nearly 3,000 horsepower, counter-rotating propellers eliminating torque, concentrated nose armament with 450 caliber machine guns and one 20mm cannon. At level flight, nothing could catch it. But in the dive, where fighters lived or died, where battles were won by whoever could strike first from above, the P-38 became something else entirely. A 7-ton coffin falling through thin air, its controls locked solid, its pilot helpless as the desert floor rushed upward at terminal velocity. Gilkey somehow survives, riding out the dive until the denser air at lower altitude gives him enough control authority to pull out, his hands trembling, his flight suit soaked through. But other test pilots won't be as fortunate. And the German pilots facing these silver twin-boomed fighters over Europe and the Mediterranean will learn to exploit this fatal weakness, diving away from combat, knowing the Lightnings cannot follow without risking their own destruction. Until Lockheed and a team of civilian aerodynamicists at the National Advisory Committee for Aeronautics refuse to accept that America's fastest fighter must choose between speed and survival. Their solution, a set of small electrically actuated flaps mounted under each wing, will transform the P-38 from a temperamental thoroughbred into a dive monster capable of speeds German intelligence will declare impossible. But the path from death trap to tactical weapon will cost lives, test the limits of wartime engineering, and reveal truths about high-speed flight that won't be fully understood for another decade. The wreckage told its own story. Twisted aluminum scattered across California terrain, a tail section separated from the fuselage, impact craters marking where components struck Earth at velocities human bodies weren't designed to withstand. November 4th, 1941. Lockheed test pilot Ralph Verdon had taken off from Burbank just 90 minutes earlier in P-38 No. 1, tasked with evaluating new servo-tab mechanisms designed to help pilots maintain control during high-speed dives. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The servo tabs were supposed to be the solution, spring-loaded devices that would multiply pilot input when control forces exceeded 30 pounds, essentially power assist for the elevator. In theory, they would allow pilots to overcome the heavy control forces that developed during high-speed dives. In practice, they worked too well. When Verdon pulled back during his dive recovery, the tabs generated forces strong enough to rip the tail completely off the airframe. He died on impact, adding his name to a growing list of test pilots killed by a phenomenon that aviation engineers barely understood. In Burbank, Clarence Kelly Johnson stared at the accident report with the kind of focused intensity that made subordinates nervous. The P-38 was his baby, the most advanced fighter Lockheed had ever built, and it was killing the people trying to perfect it. The preliminary investigations all pointed to the same culprit: compressibility, a word that sounded academic, theoretical, safely confined to wind tunnels and textbooks. But compressibility was very real, very deadly, and completely beyond the experience of every aeronautical engineer working in 1941. The problem wasn't structural failure in the traditional sense. The P-38's airframe was strong, overbuilt if anything, designed to handle tremendous loads. The problem was aerodynamics at speeds no production aircraft had ever sustained. When the Lightning dove from altitude, pushing past 400 miles per hour, the airflow over its wings accelerated to velocities approaching the speed of sound. At those transonic speeds, the smooth, predictable behavior of air broke down completely. Shock waves formed over the wing's thickest section, between the central nacelle and the engine booms. These invisible walls of compressed air fundamentally changed the pressure distribution across the entire aircraft. The center of lift shifted backward toward the tail. The smooth downwash of air that normally flowed over the horizontal stabilizer was disrupted, effectively starving the tail of the airflow it needed to function. The elevator, that crucial control surface responsible for nose-up and nose-down pitch, lost nearly all authority. Pilots described it with stark simplicity. The stick felt like it was embedded in concrete. No amount of human strength could move it. And, with the center of pressure shifted aft, the aircraft's nose pitched down even further, steepening the dive, increasing the speed, making the compressibility effects worse. It was a death spiral in the most literal sense. Once a P-38 entered this regime, survival depended entirely on whether the pilot could hold on long enough to reach denser air at lower altitude, where the increased dynamic pressure might restore some measure of control. The Army Air Forces needed the P-38. Design specifications called for an interceptor capable of climbing to 20,000 feet in 6 minutes, reaching speeds exceeding 360 miles per hour at altitude, and carrying enough armament to destroy bombers with single bursts. Traditional single-engine fighters couldn't meet these requirements. Engine technology in the late 1930s simply couldn't pack enough horsepower into one power plant to achieve both the performance and the range the military demanded. Lockheed's solution was radical. 2 engines, each with its own turbo supercharger, mounted in streamlined booms that also housed the landing gear and carried the tail surfaces. The pilot sat in a central nacelle with all guns firing straight ahead, eliminating the convergence issues that plagued wing-mounted weapons. Counter-rotating propellers cancelled each other's torque, making the aircraft more stable in climbs and turns. On paper, it was brilliant. In combat, it would prove exceptional. But first, someone had to solve the compressibility problem. John Stack arrived at Wright Field in Dayton, Ohio, with a reputation for understanding transonic flow better than almost anyone in America. A civilian aerodynamicist working for NUCA, Stack had spent years studying what happened when air approached the speed of sound. His wind tunnel work suggested that compressibility effects represented a fundamental physical barrier, not a design flaw specific to the P-38. Any aircraft fast enough and heavy enough to reach these speeds in a dive would encounter similar problems. But Stack also believed the problem was solvable. The key was understanding exactly where and how the shock waves formed, then finding ways to modify the pressure distribution to maintain control authority. He requested access to Lockheed's wind tunnel facilities and permission to test scale models of the P-38 at transonic speeds. Kelly Johnson, recognizing that his own facilities were inadequate for this work, agreed immediately. Throughout late 1941 and into 1942, Stack's team ran hundreds of test sequences. Miniature P-38 seconds, built to precise scale, were mounted in wind tunnels, capable of pushing air past them at speeds approaching Mach 0.75. High-speed cameras captured the formation of shock waves. Pressure sensors mapped the distribution of forces across wings and tail surfaces. Gradually, a picture emerged. The shock waves weren't uniform. They formed first at the wing root, where the thick section between the nacelle and engine booms created the greatest acceleration of airflow. As dive speed increased, the shock waves grew stronger and moved further back along the wing chord, eventually disrupting the entire flow field over the horizontal stabilizer. The tail wasn't failing mechanically. It was simply flying in dead air, unable to generate the downward force needed to counteract the nose-down pitching moment. Stack's analysis suggested a counterintuitive solution. Instead of trying to prevent shockwave formation, which seemed impossible with current aerodynamic knowledge, they should modify the pressure distribution under the wing. If they could increase the pressure under the wing near the trailing edge during a dive, they might be able to shift the center of pressure forward again, restoring the balance between wing lift and tail authority. The device that eventually emerged from this research looked almost comically simple. Small flaps, roughly 3 feet long and 18 inches wide, mounted under each wing outboard of the engine nacelles. When deployed, they would extend downward about 35 degrees, creating a local disruption in the airflow that would change the pressure distribution across the entire wing. They weren't air brakes, despite the superficial resemblance. They were dive recovery flaps, carefully shaped and positioned to restore control authority at transonic speeds. The first prototype installation took place in early 1943. Kelly Johnson's team fabricated the flaps from lightweight aluminum, installed electric actuators capable of deploying them in less than 2 seconds, and added a simple toggle switch to the instrument panel. The test aircraft would be flown by one of Lockheed's most experienced test pilots, a man whose name was already legendary in aviation circles for his willingness to fly anything the engineers could build. Meanwhile, operational P-38 squadrons were learning to live with their aircraft's limitations. In the Pacific Theater, where the Lightning was proving exceptionally effective against Japanese fighters, pilots developed tactics that avoided steep, high-speed dives. Climb high, attack fast, but always maintain awareness of airspeed. Never exceed 400 miles per hour indicated. Never commit to a dive that couldn't be controlled. In Europe, where Luftwaffe pilots were among the best trained in the world, the limitations became more costly. German intelligence had identified the P-38's dive restriction, and fighter commanders instructed their pilots to exploit it. When Messerschmitt 109 seconds or Focke-Wulf 190 seconds found themselves engaged with Lightnings, they would often initiate steep dives, knowing the American twin-engine fighters couldn't follow without risking structural failure or loss of control. The tactical implications were profound. The P-38 had been designed specifically to exploit altitude advantage. Climb above the enemy, dive down with superior speed, deliver devastating firepower, then use that speed to climb back to altitude before the enemy could react. But if the dive portion of this tactic was fundamentally unsafe, the entire tactical concept collapsed. Pilots found themselves forced into turning fights, where the P-38's size and weight became disadvantages against lighter, more nimble opponents. Lieutenant Colonel James Doolittle, who had led the famous bombing raid on Tokyo, flew several missions in P-38 seconds and immediately recognized the problem. The Lightning had the power, the armament, and the performance to dominate any enemy fighter at altitude, but its inability to safely exploit high-speed dives meant that altitude advantage could become a trap rather than an asset. If enemy fighters dove away from combat, P-38 pilots had to choose between breaking off the engagement or following into a flight regime where their own aircraft might kill them. Test pilot Tony Levier understood the stakes when he strapped into the modified P-38 on a clear March morning in 1943. The dive recovery flaps represented months of research, hundreds of hours of wind tunnel testing, and the combined expertise of Lockheed's best engineers and NACA's top aerodynamicists. But theory and testing could only go so far. Someone had to deliberately fly the aircraft into the conditions that had killed Ralph Verdun, then trust that small aluminum flaps would save them. Levier climbed to 35,000 feet over the Mojave Desert, the same airspace where Major Gilkey had survived his harrowing dive 2 years earlier. The test protocol was straightforward but terrifying. Push the nose over into a steep dive. Let the airspeed build past 400 miles per hour, past the point where compressibility normally began to manifest. Continue accelerating to 450 miles per hour, well into the regime where control authority disappeared and survival became a matter of luck. Then, at precisely the right moment, flip the toggle switch that deployed the dive recovery flaps. And pray that Stack's calculations were correct, that the pressure distribution would shift as predicted, that control authority would return before the aircraft entered an unrecoverable state. The altimeter unwound with terrifying speed. 40,000 feet, 35,000, 30,000. The airspeed indicator climbed past 350, 400, 420 miles per hour. Levier felt the familiar onset of compressibility, the stick growing heavy in his hands, the nose beginning to drop despite his efforts to maintain a steady dive angle, the buffeting starting to build through the airframe. 450 miles per hour. He was now in territory that had killed test pilots, exceeded the aircraft's published limitations, flying an untested modification that might work or might make everything worse. His right hand moved to the toggle switch. One flip of his thumb would deploy both flaps simultaneously, changing the entire aerodynamic behavior of the aircraft in less than 2 seconds. He flipped the switch. The effect was immediate and dramatic. Control authority returned to the elevator. The stick, which moments before had felt like it was embedded in concrete, suddenly responded to normal pressure. Levier pulled back gently, watching the airspeed, feeling the aircraft's nose come up, the dive angle decreasing from steep to moderate. The buffeting diminished. The horrible feeling of helplessness, of being a passenger in an aircraft determined to destroy itself, disappeared. He was flying again, not just maintaining altitude or struggling against physics, but actually flying, with precise control over pitch, roll, and yaw. The dive flaps had worked exactly as Stack predicted. They had modified the pressure distribution under the wings, shifted the center of pressure forward, restored the airflow over the horizontal stabilizer. At 470 miles per hour, a speed that should have been impossible to survive in a P-38, Levier was pulling out of his dive with normal G-forces and complete control authority. But one successful test flight couldn't validate a modification intended for thousands of aircraft and hundreds of pilots. Stack insisted on exhaustive testing at every possible combination of altitude, airspeed, and dive angle. Levier spent weeks deliberately entering compressibility conditions, each time trusting the dive flaps to bring him back from the edge. The test results consistently showed that the flaps could restore control authority up to approximately Mach 0.70, well beyond the original aircraft's safe operating envelope. The engineering analysis revealed why the modification worked so effectively. The flaps didn't significantly reduce airspeed, as traditional dive brakes would. Instead, they created a localized increase in pressure under the wing near the trailing edge. This pressure increase propagated forward through the airflow, effectively counteracting the rearward shift of the center of pressure caused by shockwave formation. The horizontal stabilizer received a restored downwash, the elevator regained authority, and pilots could execute normal dive recoveries even at transonic speeds. Production of retrofit kits began in April 1943, with Lockheed's manufacturing teams working extended shifts to fabricate components. Each kit included 2 flaps with their actuator mechanisms, complete wiring harnesses, detailed installation instructions, and a supplement to the pilot's operating handbook explaining proper deployment procedures. The first shipments were prioritized for combat units, already deployed overseas, where the modification could have immediate tactical impact. Installation proved surprisingly straightforward. Squadron maintenance crews could complete the modification in approximately 8 hours, mounting the flaps to existing hard points on the wing structure and connecting the electrical system through a simple toggle switch on the instrument panel. Pilots could deploy the flaps in less than 2 seconds, fast enough to respond to developing compressibility conditions before they became unrecoverable. Field trials began immediately with squadrons operating from bases in North Africa and the Southwest Pacific. Initial pilot reactions mixed enthusiasm with understandable caution. The dive flaps represented salvation from a limitation that had constrained tactics for 2 years. But they were also an untested modification, and combat pilots had learned through bitter experience that new systems could fail at the worst possible moments. The first combat use of dive recovery flaps occurred during an engagement over Sicily in May 1943. A P-38 pilot, diving to attack German transport aircraft, deployed the flaps while accelerating past 450 miles per hour. The recovery was smooth, controlled, and allowed him to press his attack before climbing back to altitude. Word spread quickly through lightning squadrons. The modification worked. The dive restriction was gone. But early success couldn't prevent the inevitable complications that accompany any wartime modification program. Supply lines stretched across thousands of miles, were vulnerable to enemy action, mechanical failure, and simple bad luck. The most significant setback occurred in early June, when a Douglas C-54 Skymaster transport aircraft carrying 200 dive flap kits was shot down over the Mediterranean. An RAF pilot, unable to identify the transport positively, mistook it for a German Focke-Wulf Condor and opened fire. The transport crashed into the sea, taking with it enough kits to retrofit an entire fighter group. The loss delayed modification programs for several squadrons and highlighted the vulnerability of specialized equipment to the chaos of war. Additional complications arose when some maintenance crews reported installation errors that rendered the flaps ineffective or, in rare cases, actually dangerous. One pilot discovered his flaps deployed asymmetrically during a dive, creating a rolling moment that nearly caused him to lose control. Investigation revealed an improperly secured wiring harness that had allowed vibration to sever electrical connections. Squadron maintenance officers began developing quality control procedures that exceeded manufacturer recommendations. Technical Sergeant Mike Kowalski of the 55th Fighter Group created a detailed checklist requiring 3 separate inspections before any dive flap installation was considered complete. His procedures were eventually adopted by other units and incorporated into official maintenance manuals, but not before several more installation-related incidents highlighted the critical importance of proper technical execution. Combat reports from units equipped with dive flaps began documenting tactical advantages that validated the modification's effectiveness. P-38 pilots were once again willing to exploit their aircraft's altitude advantage, diving from high altitude with confidence that they could recover safely even at transonic speeds. The psychological impact was as important as the tactical advantage. Lightning pilots were no longer flying aircraft they fundamentally distrusted, but rather machines that could exploit their full performance envelope safely. By autumn 1943, several hundred P-38 seconds operating in combat theaters had been equipped with dive recovery flaps. Production aircraft coming off Lockheed's assembly line still lacked the modification, as the 14-month delay between prototype testing and production integration meant that field retrofit remained the only option for aircraft already deployed. But plans were underway to incorporate the flaps into the production line, eliminating the need for field modifications and ensuring that every Lightning delivered to combat units would have full dive capability from the day it entered service. The transformation of the P-38 from a temperamental fighter with fatal limitations into a true high-speed interceptor was underway. But the real test would come not in controlled flight tests or limited combat trials, but in the sustained, brutal air battles over Europe and the Pacific, where American and Axis forces were locked in a struggle that would determine the war's outcome. The afternoon of September 14, 1943, 32,000 feet above the Solomon Islands, Major Richard Bong rolled his P-38 inverted and pulled through into a near-vertical dive, chasing a formation of Japanese Zero fighters climbing to intercept American bombers. The airspeed indicator swept past 400 miles per hour, then 430. In an unmodified Lightning, this would be the moment when compressibility transformed his aircraft into an uncontrollable missile. But Bong's P-38 carried one of the first production dive flap installations, shipped from Burbank just 3 weeks earlier and installed by squadron maintenance crews working through tropical heat and sudden rainstorms. At 460 miles per hour, Bong felt the familiar onset of control stiffening, the first hint that shock waves were forming over his wings. His right thumb found the toggle switch mounted on the control yoke. One decisive motion deployed both dive flaps simultaneously. The effect was immediate. Control authority returned. The nose, which had been beginning its deadly downward tuck, stabilized under normal pressure. Bong continued his dive, accelerating to nearly 500 miles per hour as he closed on the 2022 unsuspecting Japanese fighters. The Zero pilots never saw him coming. At that speed, traveling vertically downward through thin air at altitude, Bong's P-38 was simply too fast for visual detection until he was already in firing position. His concentrated nose armament, 4 50 caliber machine guns, and 1 20mm cannon converged on a single Zero. A 3-second burst disintegrated the enemy fighter. Bong continued through the formation, then deployed his flaps again to pull out of the dive in a smooth arc that carried him back to altitude before the remaining Japanese pilots could react. For the first time in 2 years, a P-38 pilot had deliberately entered the transonic dive regime, exploited it tactically, and emerged with a confirmed kill and complete control of his aircraft. The transformation from defensive limitation to offensive weapon was beginning, but the path from isolated success to widespread tactical doctrine would require more than just functioning dive flaps. It would require fundamental changes in how pilots thought about their aircraft, how maintenance crews serviced them, and how commanders planned missions that exploited this newly unlocked capability. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By late October 1943, approximately 400 P-38's operating in combat theaters had been equipped with dive recovery flaps through field retrofit programs. The installations proceeded unevenly. Combat units in the Southwest Pacific, where supply lines stretched thousands of miles across hostile ocean, sometimes waited months for kits that had been shipped but lost to enemy action or simple logistical failure. Units operating from bases in North Africa and Italy received priority shipments, but harsh desert conditions created their own challenges. Sand-infiltrated actuator mechanisms, extreme temperature, variations caused electrical connections to fail. Maintenance crews adapted, developing improvised solutions that kept the systems functional under conditions Lockheed's engineers had never anticipated. The 55th Fighter Group, operating from bases in England, received their dive flap kits in late October. Installation began immediately, but European weather complicated everything. Freezing rain grounded aircraft for days. Maintenance hangars, unheated and exposed to North Atlantic storms, became miserable workplaces where mechanics struggled with frozen tools and numb fingers. Yet the work continued because everyone understood what was at stake. The bomber offensive against Germany was reaching its crisis point. 8th Air Force B-17 Flying Fortresses were attempting deep penetration raids into the Reich, targeting ball-bearing factories, aircraft production facilities, and oil refineries that kept the German war machine functioning. But without adequate fighter escort, these missions were becoming death sentences. The Schweinfurt raid of October 14th, just one day before the 55th Fighter Group flew their first combat mission, had cost 60 B-17 destroyed and another 17 damaged beyond repair. Nearly 600 American airmen were dead, wounded, or missing. P-38's were supposed to help solve this crisis. Their twin-turbo supercharged engines could maintain power at altitudes where other fighters gasped for air. Their range, with drop tanks, exceeded that of any single-engine fighter then available. But the compressibility problem had neutered their effectiveness. German fighter pilots knew that Lightnings wouldn't follow them into steep dives, so they developed tactics that exploited this limitation ruthlessly. The dive flaps promised to change this equation, but promises meant nothing without combat validation. That validation came on November 26, 1943, during an escort mission to Bremen. The 55th Fighter Group, flying P-38's, equipped with freshly installed dive flaps, encountered a large formation of Messerschmitt 109 at 28,000 feet. The German fighters, following standard doctrine, attempted to break away by diving steeply toward the deck. This time, the P-38's followed. Pilots who had spent months avoiding steep dives suddenly found themselves accelerating downward at speeds that would have been suicidal just weeks earlier. The dive flaps deployed with satisfying mechanical precision, restoring control authority, allowing aggressive pursuit of enemy fighters who expected to escape unopposed. 3 Messerschmitts went down in flames. The remaining German pilots, confronted with a tactical reality they hadn't anticipated, broke formation and fled. The engagement lasted less than 10 minutes, but its implications rippled through both American and German intelligence services for months. 8th Air Force commanders began incorporating high-speed diving attacks into standard escort fighter doctrine. German intelligence officers received troubling reports of P-38's performing maneuvers that exceeded their documented capabilities. Luftwaffe pilots who had grown comfortable with certain tactical assumptions found those assumptions suddenly invalid. But success in isolated engagements couldn't mask ongoing challenges with dive flap deployment and reliability. The March 1944 disaster, when RAF fighters mistakenly shot down a C-54 transport carrying 200 dive flap kits intended for European theatre P-38's seconds, highlighted how vulnerable specialized equipment remained to the chaos of total war. 6 fighter groups had been scheduled to receive those kits. Their installation timelines were pushed back months, forcing pilots to continue operating with unmodified aircraft while knowing that a solution existed but remained inaccessible. The psychological impact was significant. Pilots who had heard about dive flaps, who knew that other squadrons were using them successfully, found themselves flying aircraft they understood to be obsolete. The resentment this generated filtered into after-action reports, pilot complaints, and eventually congressional inquiries about procurement failures and supply chain bottlenecks. Lockheed test pilot Tony LaVere arrived in England in April 1944 as part of a morale-boosting tour designed to demonstrate dive flap capabilities directly to combat pilots. Flying a specially modified P-38J equipped with the latest production standard dive flaps, LaVere conducted demonstration flights at multiple fighter bases. His routine included maneuvers that had been impossible in unmodified Lightnings. Vertical dives from above 30,000 feet, accelerating past 500 miles per hour, then executing controlled recoveries that subjected both aircraft and pilot to sustained G-forces well within design limits. Pilots watched these demonstrations with mixed emotions: relief that the modification actually worked as advertised, frustration that many of them still lacked access to the upgrade, and renewed determination to exploit every tactical advantage once their own aircraft received the modification. LaVere's tour coincided with the arrival of production P-38J-25 models, the first Lightnings to roll off the assembly line with factory-installed dive flaps as standard equipment.